The second approach in finding roots of nonlinear equations is the bisection method. Learn it here in Numerical Solutions to see problems. Before delving with an example, let's differentiate bisection from the previous method first. Say that we have a curve drawn on the Cartesian plane, where the root is as indicated. When we were working on incremental search method, we actually have to divide the interval into desired increments and compute in order to know which smaller interval to use in the next iteration. Although admittedly, this method is simple, it is time-consuming, so the bisection method shortens the procedure a little bit. In this approach, the concept is to cut the interval into half and totally disregard the irrelevant half. So we take x of 0.5 and then drop the first half as the root is found on the second half anyway. The problem to illustrate this method includes f of x is equal to 2x cubed minus 4x squared plus 5. We are to look for the root nearest the origin, on the negative side, and we would only need 3 decimal zeros, but still, the initial values are whole numbers. So just like any other method, we start with the initial values, using the given instructions. So we try x of 0. The function then becomes twice of 0 cubed minus 4 of 0 squared plus 5. This is simplified as 5. When x is plugged as negative 1, the function turns into 2 times negative 1 cubed minus 4 of negative 1 plus 5, which is negative 1. We got a sign jump. Illustrating these coordinates, at x equal to 0, y is 5. And when x is negative 1, y becomes negative 1. Connecting these 2 points, we can identify the location of the root. So how does the bisection method work? First, identify the 2 points. At x equal to negative 1, y turned out as negative. Then, when x is 0, y turned out as positive. Because we needed to disregard half of the interval, we take the average of the x values. So half of 0 plus negative 1 is negative 0.5. If this is substituted in the function, y turns out as twice of negative 0.5 cubed minus 4 of negative 0.5 squared plus 5, which gives 3.75. And this is positive. This means that the positive limit will be replaced. So instead of using 5, we use 3.75. This is the new positive limit, disregarding the rest of the interval. If we zoom in the remaining interval, we have the left limit, which was the negative y limit at x equal to negative 1. The function is also negative 1. The right limit, which we tagged earlier as positive, is at x equal to negative 0.5, and its y is positive 3.75. Using the bisection method, we take half of the interval, which is computed by taking the average, and that is half of negative 1 plus negative 0.5, which is negative 0.75. Now we take the y value of the curve at this point, so place negative 0.75 into the function, making it twice of negative 0.75 cubed minus 4 times negative 0.75 squared plus 5, which is simplified into 1.90625, and it is positive. which means negative 0.75 is the new right limit of the interval. So all the rest of the span will be disregarded. It would be quite tedious to keep on illustrating the small intervals in each increment. So instead of illustrating, we use table form. In the table, there are columns for the left limit, which in this case is the negative y limit, the right limit, which is positive, the midpoint or the average of the limits, and the function or the y value at the midpoint. Denote each column for easier calculations later. The left limit's labeled A, whereas B for the right limit. The average is tagged as C, and its function is f of C. Place all computed values earlier in the table. From the initial values, we have the left limit as negative 1, and the right was 0. We took their average, which was negative 0.5, and placed this into the function and got positive 3.75. We disregarded half of the primary interval and zoomed in the remaining half. So the left limit was still negative 1, but the new right limit is now negative 0.5. We also took their average, which was negative 0.75, and have this plugged into the function, which gave us positive 1.90625. Note that the sign of f of c determines which half is to be considered. With the recent f of c as positive 1.90625, the value of c replaces the right limit. The left limit will just be carried out as it is. Then we complete the rest of the iteration by taking the average, and that is half of negative 1 plus negative 0.75, giving negative 0.875. Use this value into the function, and have twice of negative 0.875 cubed minus 4 times of negative 0.875 squared plus 5. This gives f of c as 0.597656, and it is positive. Now before we fill out the rest of the table, take note that from the column of left limit to average of limits, all figures are x values. The last column, labeled as f of c, is a y value. We can now proceed with the iteration using the table. From the third row, check the sign of f of c. It is positive. This signifies that we should replace the positive limit, which is the right limit. So move the value of c to b, and drop down the same value of a. With a and b already identified, we take their average, and that is half of negative 1 plus negative 0.875, which is negative 0.9375. This is the new midpoint coordinate, and its y location is taken by substituting this value into the function. Thus we have twice of negative 0.9375 cubed minus 4 times of negative 0.9375 squared plus 5. The y-coordinate when x is at negative 0.9375 is at negative 0.163574. This completes the fourth iteration, although f of c is still far from 0. Continue the iteration to the fifth row. The sign of f of c is negative. This means that c should replace the negative limit, which is the left limit, and the right limit would just be carried from the former value. After which, take the average of a and b. That would be half of negative 0.9375 plus negative 0.875, which is negative 0.90625. Place this in the function, making 2 times negative 0.90625 cubed minus 4 times negative 0.90625 squared plus 5, which gives positive 0.22626. Work on the next iteration as we need to reach 3 decimal zeros. Having a positive f of c, which is negative 0.90625, should replace b, and a would remain the same as negative 0.9375. Now take the average of a and b, that is negative 0.9375 less negative 0.90625 all over 2, and this gives negative 0.921875. Plug this into the function, making 2 times negative 0.921875 cubed minus 4 times negative 0.921875 squared plus 5, resulting to positive 0.03367. With the last value of f of c being positive, we replace b with negative 0.921875. A is still negative 0.9375. Complete the iteration by taking the average of a and b. C is then computed as half of negative 0.9375 plus negative 0.921875, giving negative 0.929688. Substitute c into the function to have twice of negative 0.929688 cubed minus 4 times of negative 0.929688 squared plus 5, where f of c becomes negative 0.06437. At this stage, we already reached 1 decimal zero, so a few more iterations to go. With negative 0.60437 for the previous f of c, replace a with negative 0.929688. b will just be carried from the former value of negative 0.921875. Then take the average again, half of negative 0.929688 plus negative 0.921875, resulting to negative 0.925781. Place this value into the function to have f of c as negative 0.01520. For the next iteration, f of c being negative will help us realize that a should be replaced by negative 0.925781. b at negative 0.921875 remains the same. The average after which is computed as half of a plus b, which ends as negative 0.923828. Plug this into the function and get 2 of negative 0.923828 cubed minus 4 times negative 0.923828 squared plus 5, giving 0.00927. We can see progress here as we already reached 2 decimal zeros. With the last f of c as positive, take c of negative 0.923828 and replace b. Then carry out negative 0.925781 to the current iteration. Next is to take half of a and b together, which gives negative 0.924805. Place this into the function and have twice of negative 0.924805 cubed minus 4 of negative 0.924805 squared plus 5, resulting to negative 0.00296. The next iteration follows the same process. Take note of the negative f of c, saying that c should replace a. Then b is carried down. The average of a and b is half of negative 0.924805 plus negative 0.923828, which gives negative 0.924316. F of c is then computed as twice of negative 0.924316 cubed minus 4 times of negative 0.924316 squared plus 5, resulting to positive 0.00316. For the next iteration, having a positive f of c makes it clear that c of negative 0.924316, we replace b. A stays the same at negative 0.924805. The average of A and B results to negative 0.924561. Then plug this average in the function, which becomes 2 times negative 0.924561 cubed minus 4 times the square of negative 0.924561 plus 5, where f of c becomes 0.00010. This finally provides 3 decimal zeros, as required by the problem. So we can then say that the root of the function is negative 0.924561.